Hello, everyone. Today, we're going to discuss a classical but complex problem in mathematical control theory. How do you control a system of vibrating flexible beams? You can imagine aircraft wings, robotic arms, or bridge spans. This can be molded as flexible beams. Now consider two such beams connected together. What if you could control the anti-system's vibration not from the ends? We usually do that, but right at the point joint where they meet. This is precisely the problem discussed in J.P. Ma's 1997 paper, Controllability of Coupled Flexible Beams with Control Applied at Coupled Point. This paper isn't just theoretical, it has direct implications for engineering more stable aerospace structures, precision robotics, and resilient civil infrastructure. The key achievements of this paper are: 1. Established necessary and sufficient conditions for approximate controllability. 2. Proved controllability depends on single parameter, the coupling point location. 3. Provided conditions for exact controllability using sophisticated mathematical tools. Let's see the introduction part. System 1 to 4. This part, equation 1, displays two beam segments on intervals 0C and C1. You can imagine this is beam 1 and this is beam 2. They connect at x equals c, with boundary conditions given by 2, initial conditions given by 3. Then in 4, that's the control functions defined from different elements. F equals F1, 2, 3, 4. They applied at the cut point. Here, alpha is a positive constant. We will discuss later what is really meaning in physics. F1 represents, in kinetical point of view, F1 is displacement gap, F2 is rotation gap, F3 is bending moment gap, F4 is shear force gap. Let's discuss alpha. Alpha we call damping coefficient. Its law influences the overall dynamic response of the beams. A higher alpha represents stiffer or more damped system. This will result in less deformation and slower vibrations. When alpha is low, it means more flexible or less damped system. It will allow for great deformation and fast vibrations. So, in real-world applications, RFI could be addressed to model different materials and environmental conditions. Let's pay attention to this part. Law of UX2 dt. This term describes how the bending of the beams evolves over time. It is crucial for understanding the dynamic response of beams to external forces or control inputs. In control applications, this term helps in designing control strategies to stabilize or optimize the beam's behavior. In real-world applications, we see flexible beam system can be used to aircraft wings and aerodynamic forces, bridge expanse vibrations from traffic and wind, flexible robotic arms for precise movement, wind turbine blades experiencing dynamic blows. In full, Fi are control functions in space V, H0202. Here, H202 denotes the usual Sobolev space, and Fi refers I's derivative of F. As we pointed, F1 we can consider is a gap in displacement at x equals c between beam 1 and beam 2. F2 in rotations, F3 in bending movements, F4 for shear force. Let Wi equals F equals F1, 2, 3, 4 belongs to W equals V times VV. Fg equals 0, Ji not equals J, Ij equals 1, 2, 3, 4. By this definition, we see that control F equals F1, F2, F3, F4 is of type I if F belongs to Wi. Then we assume that H is Hilbert space L20C times L2C1 with an inner product defined by this equation. We identify U equals U1, U2 belongs H with a function Ux, U1, U2 for X belongs to 0, C, and X belongs to C to 1 respectively. We will consider exact controllability and approximate controllability for the system 1 to 4 in a Hilbert space X equals E times H, where E is also a Hilbert space with a dense and continuous embedding E belongs to H, such that for every initial data U0, V0 belong to X, and F belong to W, there exists a solution UXT of the system 1 to 4 with U and UT in X. The definitions are given as follows as definition 1. Definition 1 expresses the type of the exact controllability in the system. Let D be a subset of X times X. The system 1 to 2 is called exactly controllable of type I in D if for every initial data U0, V0 and final data U1, V1 with U0, V0, U1, V1 belongs to D, there exists a control F belongs to Wi such that the corresponding solution of 1 to 4 satisfies the final condition UXT equals U1X and UTXT equals V1X. Definition 2. We said that system 1 to 4 is approximately controllable of type I in X if for every initial data U0, V0 and final data U1, V1 in X and any absolute small absolute larger than 0, there exists a control F belongs to Wi such that the corresponding solution UXT of one system 124 there is control such that the corresponding solution UXT of 124 satisfies the inequality 6 why this norm denotes the norm on X. Let's go to the second part, the main results and the approval. In this section, we will give our main result on the exact controllability and the approximate control for the system 1 and 2, and also provide the pros of them. For the exact controllability, we reduce it to movement problem, which have been studied by reference 1. For the approximate controllability, we use methods similar to those employed in 2 K-August work. The controllability of system 1 to 4 in the case of alpha equals 3 have been treated by 4 or not. The result of this paper are extension of his work in case of alpha larger than 0. Let F equals F1, 2, 3, 4, given in W and U0, V0, X. A solution UXT of system 1 to 4 can be expressed finally as X7. This splits the solution into YXT, handle homogeneous system dynamics. In this system, the control part can be expressed directly in 8. So you can see system 1 to 4 can be replaced by system 8 to 9. The existence and uniqueness of a solution to the initial boundary value problem 8 to 9 can be shown by applying the semigroup theory. So now we are going to do some establish some tools. Apply the function analysis knowledge to solve the solutions of system 8 to 9. So in H, we define an operator A0 with domain dA0 as follows, given by 10. The operator A0 is positive and self-adjoint in H with a compact reservoir weight. Also, the operator A0 has a positive square root A0 1 over 2, such that it is easy to conclude that dA0 included in dA0 1 over 2. Furthermore, there exists a sequence of Fn values, lambda n, for the operator A0 1 over 2, with lambda 1 smaller than lambda 2 series, lambda n approaching infinity, 1n become going to infinity. And corresponding Fn functions Cn, n equals 1 or 2, 3, form an orthonormal basis in H. This is the calculation result. Lambda n equals n squared pi squared, and phi s equals root sine root n lambda nx. If we put 11 with the initial conditions, then A to 9 can become 12, 13. So we will see The system solution of 8 to 9 can be expressed by system 12 to 13. Then we have the lemma 1. A is an infinitesimal generator of a contraction semigroove in X. By lemma 1, we can define definition 3. U, T, and VT can be defined as strict solution to system 12 to 13. Also, we can define a mild solution, 16, for system 12, 13. So the solution can be expressed in the formulation of given by 17, which means that system 102 can be replaced by system 12, 13. Then, from now, we will consider exact controllability and the approximate controllability for the system 12, 13. So 12, system 12 and to system 12, 13 are equal to system 1 to 4. Definition 5 and definition 6 can be equivalent to definition 1 and definition 2. This will come to the lemma 2. Then we begin to define a reachable set of type I as follows. 18. Then we come to a conclusion lemma 3. Approximate controllability if and only if reachable set is dense in X. Then we come to the lemma 4. Explicit semigroove formulas for these 3 damping cases, alpha larger than 1, alpha equals 1, and alpha smaller than 1. Of course, alpha larger than 0. Alpha larger than 1 is over-dampened. Alpha equals 0, critically damped. Alpha smaller than 1, under-damped. Model analysis breaks complex motion into decoupled vibration modes. Then we come to the lemma 5. System is axiomatically controllable if only if specific coefficient sequences are entirely non-zero. This is the core technical proof, lemma 5. Build the base to give the conclusion of the theory 1 and theory 2, the main result of the paper. In lemma 5's verifications, sophisticated analysis including duality arguments, uniqueness of series expansions, analytical continuation. This providing the result of lemma 5. Then, with the work in the lemma 5, we finally reached the theorem 1. This stunning conclusion, controllability depends on number theory. For control types 1 and 3, displacement and movement, controllability if and only if C is irrational or C equals P over Q with P is even or Q is odd. For control types 204, rotation and shear force, controllability depends on if and only if C is irrational. This is the main conclusion for the approximately controllable of the type 1 O and type 3. This is the conclusion of type 2 and type 4. Finally, we have theorem 2. Exact controllability possible but restricted to smooth states, exponentially decaying Fourier coefficients. We use infinite dimensional movement problems to serve the provided result of theorem 2. Conclusion is a powerful demonstration of abstract mathematics solving concrete engineering problems. Summary of this paper provides a complete answer to coupled beam control. Whether you can control depends on the arithmetical nature of the coupling point C. How precise you can control depends on state smoothness. Measure orderability shows power of operator theory and spectral analysis. The results are both mathematically elegant and practically significant for modern engineering applications. As we provide at the very beginning, you can use them in the real-world applications such as aircraft wings, bridge spans, flexible robotic arms, and wind turbine blades. Acknowledgement. The author would like to express his full gratitude to this paper, advised Professor Kunio Tsujioka, Director of Department of Mathematics, Faculty of Science, Saitama University, back to 1990s. He also like to thank Dr. S. Onali for his valuable works, which helps also to complete this paper. Dr. S. Onali's work dealing with alpha equals 0. Finally, also thanks a lot to the referee for his helpful recommendations, especially for a skillful induction in the proof of lemma 5. These are references. Thank you for watching this video. If you have any problem, any questions, please leave your comments.